In the last video, we did a graphical analysis of the fundamental theorem of calculus. I'll cover this up. Where we looked at graphs and we tried to predict what our original function was by taking the cumulative area function of whatever the derivative was. Now, let's look at it algebraically. So, in this case, we're asked to find the derivative of g, where g is a cumulative area function. G is the integral from 0 to x of sine of t dt. So I'm thinking if this is my derivative, if I wanted to, I could graph sine x. I could picture how x increases, how do those pieces of area increase, and then I could estimate what my g function looks like, and then take the derivative of that. Or we can actually just directly apply the fundamental theorem of calculus part 1. So I'm going to write that, apply fundamental theorem of calculus part 1. And what does the fundamental theorem of calculus part 1 say? It says that if this is my function g, and it's given by this type of cumulative function, that g prime is equal to this function evaluated as x, meaning that I really don't have any work to do. By Leibniz notation, the derivative of my g of x function is equal to the derivative of this integral, 0 to x of sine of t dt, and I don't have to do any work. I can directly apply the theorem, and it tells me that the derivative of my g function is equal to this function evaluated at x. And I'm done. Boom. So there was no work involved in that, right? It's just a direct application of the theorem. Here's an example where a little more work is involved. So this is almost exactly the same problem. Maybe I can put this on the same screen at once. Yeah, it's almost exactly the same problem. Here's my g of x function. But here, instead of integrating from 0 to x, I'm integrating to 0 to x squared. Now, how does that affect this? What's the difference here? The difference is that instead of growing sort of at a linear rate when I'm thinking of accumulating this area, it's growing much, much more rapidly, right? It's growing at a rate of an x squared. And in order to be able to evaluate this, we do apply the fundamental theorem of calculus, but we're going to have to use chain rule. That this function looks a lot like this function. The only difference is, instead of having an x value, I'm thinking of it as plugging in an x squared value instead. So if I want to take the derivative of g of x squared, I'm going to have to apply chain rule. This is a composition of functions. And recall from derivative calculus, that's going to be the derivative of the outside function times the derivative of the inside function. And in this case, the derivative of the inside function is the derivative of x squared. So let's break that into pieces a little more slowly. The derivative of the outside function is exactly what we found above, that the outside function with an x in it is just going to give us the outside sine of, but not x. The derivative of the outside function we still evaluate that value, but we're going to have to multiply it by the derivative of the inside function, which is 2x. So the conclusion is, anytime I'm applying fundamental theorem of calculus, but I have a variable as one of the bounds, I'm going to have to apply chain rule. And it really is exactly what you want it to be. The derivative is given by this interior function evaluated at x squared, but you have to remember to multiply by the derivative. So this 2x piece here is dx of the x squared, which was our upper bound.